Welcome back to the workshop for our last example on power series. What we want to do for this example is actually determine the interval of convergence for f, a function which is defined as a power series. We also want to find the interval of convergence for its derivative and for the integral of that function. So the main thing that we want to realize, making our work relatively short, is that the radius of convergence is the same for f, f prime, and the integral of f. That means that once we've identified where it's centered and what the radius of convergence is, all we have to do is test endpoints for each of the three different functions. I leave it to you to identify that the series, the power series, is centered at c equal to 3, and that the power series has a radius of convergence of 1. So I'm telling you these are where it's centered and what the radius of convergence is. I ask that you go ahead and investigate that for yourselves and confirm that those are both correct. So when we want to consider the original function, f of x, we would want to test x equal to 3 minus 1 and x equal to 3 plus 1, the two endpoints of the interval. We want to find that the series will either converge or diverge. If the series converges, we include the endpoint, and if the series diverges, we do not include that endpoint. So for x equal to 3 minus 1, that is x equal to 2. 2 minus 3 is negative 1. So this is just the series, the power series. Again, 2 minus 3 is negative 1. So negative 1 to the n plus 1 divided by n plus 1. Let's see, I didn't give the bounds for the summation in this case. They should have been from n equals 0 to infinity. And you'll find that this is just the alternating harmonic series. So this converges. And then we also want to look at when x is equal to 3 plus 1, so 4. 4 minus 3 is a positive 1, so that's 1 to the n plus 1 power, which is just 1, divided by n plus 1. This is just the harmonic series, so this would diverge. And we find ourselves the interval of convergence to include 2, but not include 4. So in this case we have include 2, but do not include 4. That is our interval of convergence. Now our remaining functions, f prime and the integral of f, of course we have to find out what those are, and then the interval of convergence will look similar, right? It's going to go from 2 to 4, but it may or may not include the endpoints. So I can add in 4, or I might take away 2. Either is possible. All right. So we want to identify what the derivative of our function is. Now, because we can, when we take derivatives, if I have the derivative of f plus g, I can take the derivative of f and then add the derivative of g. So with that idea, I can extend that to just say that the derivative of f is just the derivative of each one of these terms, or the sum of the derivatives of those terms. So this is equal to the sum. So n is just a constant in each case. So we use the power rule, bring the power down in front, n plus 1 times x minus 3 to the n. Actually, let me just erase that, leave it just like that. A moment, again, focus on the n plus 1 being out front. That will cancel completely with the n plus 1 in the denominator, leaving us with just x minus 3 to the nth power. Now, once I have this, I again am testing the exact same points. Test x equals 3 minus 1, and test x is equal to 3 plus 1. Of course, if you just wrote 2 and 4 there, that would be perfectly acceptable. I'm just trying to emphasize that we're taking the point where the series is centered, and we are subtracting the radius and adding the radius to get our bounds for the interval of convergence. Excellent. So once I'm here, I want to take a look at my two resulting series. So when x is equal to 3 minus 1 is 2. 2 minus 3 is a negative 1, so I just have a negative 1 to the nth power. And of course, this diverges. And then I also want to take a look at when x is equal to 3 plus 1, so 4. 4 minus 3 is 1. 1 to any power is still 1. And of course, this series diverges. So I do not include either one of the endpoints to give me an interval of convergence. From 2 to 4, that does not include 2 and does not include 4. Excellent, that's easy enough. And then of course we want to do similarly for the integral of the function. We can, when we take the integral of the sum of two functions, we can then take the sum of the two integrals. So sum of f plus sum, we can take the integral of f plus the integral of g. So extending that, we can just simply take the integral of each one of these terms in our series. And when I take the integral, I'm just using the power rule again because n plus 1 is a constant. So I increase my exponent and divide by the new exponent. So I'm left with the sum. I have x minus 3 to the n plus 2 because I've increased my exponent by 1. But once I've increased the exponent, I also need to divide by that new exponent. So I have x plus 2 in the denominator. Sorry, not x plus 2, n plus 2, as well as n plus 1. Excellent. So I divide by my new exponent, and I already had a factor of n plus 1 there. Still testing the same points. X equals 3 minus 1, and x equals 3 plus 1. That's going to give me the series. When x is equal to 2, 2 minus 3 is a negative 1, so this is negative 1 to the n plus 2 divided by n plus 2 times n plus 1. Now you might not know the convergence or divergence of this right off the top of your head, but if you were to compare this, actually not even a comparison is needed in this case, you could actually just use the alternating series test to find that this converges. And you can, let's see, for the next series where we use x is equal to 4, 4 minus 3 is 1, so we just have 1 over n plus 2 times n plus 1. There we go. Now we could use the comparison, a comparison test, so either the limit comparison test or the direct comparison test. In fact, you could even use the ratio test. Oh, actually, you know what? The ratio test would be indeterminate. So, but you can use the limit comparison with a p-series or a direct comparison. I suspect. Let's see, subtract makes it bigger overall. Yeah. So you could also do a direct comparison with a p-series to find that this also converges. Excellent. So once we've done that, that gives us the interval of convergence. It is again from 2 to 4, but because the series converges when x is equal to 2 and when x is equal to 4, we actually get to include both endpoints. So we have our interval of convergence for each of the 3 cases that were asked for. Thank you again for joining me here in the workshop. I look forward to seeing you guys again soon. Have a great day.